Hello everyone. So hopefully you are doing well during this crisis. Last time we were discussing about the Maxwell's equation. We had done a great review about that. So let me recall our findings. So these were the Maxwell's equations for the case inside a media having rho and the J as the charge density and the current densities. So this is the Gauss's law. Then we had del cross E, the curl of E, plus 1 over C, del A by del B by del T. This is 0. The analog of the Gauss's law for magnetodynamics case is del dot B is 0. That says that the B is divergenceless. And also we have del cross B, the curl of B, plus 1 over C del D by del T is equal to 4 pi by C J. So remember, rho and J are the charge and current densities. Rho and J are the charge and current densities. B, D is epsilon times E. Epsilon is the permittivity. H is B by mu. Mu is the permeability of the medium. And other than these things, we had another interesting relation. That was J is proportional to sigma E, which is the Ohm's law. So let me start by giving the equation numbers. So this is 1.1, 1.2, 1.3, 1.4, and I will call them as 2. So these are all equations 2. Using these equations, we had also found the equation of continuity, which was the following. So because we have both charge and the current, electric and magnetic field present, therefore we have del rho by del T. The rate of change of charge density is divergence of the current density. So this relation should also hold. So this is all we had discussed during the last lecture. Now we want to solve these B's and E's, the magnetic field and the electric field, in terms of certain functions of space as well as time. So now, if we look at equation number 1.3, what does it say? It says divergence of B is 0 as del dot B is 0. So therefore, this means if we write B as curl of some other vector, this relation should also hold, again hold. So this immediately implies that B could be expressed as the curl of some other vector. And this other vector is referred as the vector potential. Okay, I will talk about this later. So let me write this as equation number 4.1. Now, let us check what should be the analogous form of E. So once again, remember that when we are talking about the electrostatic field, the conservative nature of electric force tells that E should be del cross E 0. Okay, so for electrostatic case, what we had, the del cross E was 0. And that means E should be expressible in terms of gradient of some scalar function of space and time. So this means E would have been gradient of psi. Okay, and for some special reason we essentially put a negative sign in front of this. Okay, so this has been the case. Now let us try to put this value over here, and now because we are talking about the electrodynamic case, so that means we have a B del V by del T term also present over here in the equation number 1.2. So we need to make our potential such that this equation 1.2 still holds. So that means we need to improve the form of E is equal to minus del psi. So as we are discussing dynamic electromagnetism 1.2 must hold. So this means, let's see what is 1.2. This is del cross. What we have is minus del of phi plus 1 over c del by del t of curl of A, which is the value of B. So from here onwards, we could express this whole thing as the curl of the whole function. So therefore, we could write this as gradient of phi, and then we could also write this whole thing as the 1 over c del A by del T, and that whole thing should be 0. So this means in order to compensate this thing, our gradient must have a term which bears a negative sign but have the value same as this. So this immediately tells that my E should be minus of gradient of psi minus 1 over c del A by del T. Okay, so we have 4.1 and 4.2. So these 4.1 and 4.2 gives the value of electric and the magnetic field in terms of the vector and the scalar potential. Okay, so 4.1 and 4.2 gives B and E in terms of scalar and vector potentials phi. So basically this is function of r and time, and A RT. Okay, so now this is all about the vector and scalar potentials. Now let us talk about something more interesting. So these are called the gauge transformations. Okay, so let us check this equation. B is gradient of the B magnetic field is written as curl of A. And now because this is curl of A, so no matter whether we write curl of A or it could also be written as del cross the curl of A plus gradient of some other function which is essentially a scalar. Okay, some other functions of R. So this means that V would instead, so this means that A could be replaced by A plus gradient of psi. Okay, so this is the equation for 5.1. So A is, instead of writing A, if we could write that A goes to A prime C, that is A plus gradient of xi. Now because A could move to A prime, so therefore phi should also get corrected, so that our equation of motion, our equations or the Maxwell's equations remains unchanged. So that is ensured by checking these relations against 4.2. So let us put this value, the new value of A, in equation number 4.2. So using A prime, A goes to A prime in 4.2. So let us do that. So this is going to give you minus gradient of psi minus 1 over c time derivative of A, which is A plus gradient of the new scalar function. Okay, so now once again, if we try to write this thing correctly, what we will write, minus tan of psi, and then minus is here as well, so we will have plus 1 over c del xi by del t, and then 1 over c del a by del t. So this immediately tells that our phi should transform in such a manner that it should be able to adjust this extra factor, extra term 1 over c del xi by del t, and therefore we get phi prime should go to phi prime, which is phi minus 1 over del xi by del t. So this is my equation number 5.2. So equation 5.1 and 5.2 are called the gauge transformations. What do I mean? I mean when I under phi goes to phi and A goes to A prime, Maxwell's equation remains invariant, and therefore these are also, this is called the gauge invariance, nature of the Maxwell's equation, and this is called gauge invariance. This is called gauge invariance. Now this is, xi is what? Xi is actually an arbitrary function. So now, the question we might ask, because in physics everything is settled, so therefore xi should also get settled, otherwise we might end up at getting many different values of the magnetic field as well as the electric field, which is not a feasible thing. So therefore what we need to do, we need to somehow fix this parameter by putting certain conditions on this, and those conditions are called the gauge conditions. So let us discuss the gauge conditions. So gauge conditions. So now because gauge condition, as xi is arbitrary, so this is basically xi rt. So xi is arbitrary, it could be fixed by some conditions called gauge conditions, and this is called gauge fixing. So now let me give you one interesting choice. One interesting choice is, so there are basically 2 or 3 interesting choices, but what I will be talking is the very interesting choice that is here. One is del phi plus, I'm sorry, this is del dot A, the gradient of A plus 1 over C del phi by del T. So why did we do that? Remember in B we has del cross A sort of thing, and in E we have another partial of space. So if we take del, so this will operate, this will have a time operation, time derivative, and this will have a psi derivative and phi gradient, and therefore these might get repaired. So this is called the Lorentz gauge. Okay, so and then the other choice, so this Lorentz gives homogeneous equations for phi and A. And then the second choice is the gradient of A is 0 itself, and that is called the Coulomb gauge. Okay, so let us see how the equation of motion for phi and A look like in the two respective gauges, which are known as the Lorentz as well as the Coulomb gauge. Okay, so but before that, let me check one more interesting feature of this, how gauge fixing, gauge parameter is fixed. So this is gauge fixing. So remember what we had was the following. We could transform what we will have, the gauge condition. Let me name it. So this is going to be 6.1 and this is going to be 6.2. So this is 6.1 we want to consider will become what will it become? We will have del phi prime plus 1, I'm sorry, this is del, we had del dot A plus 1 over C del dot B del T. So this is going to be del dot A. So this is going to be del dot A prime plus 1 over C del phi prime by del T. So this would be the transformed one. So if we write this as A plus what we had? We had A plus del of psi plus 1 over C del T of phi minus 1 over C del A by del T. This is all we have. So from here, if we try to recover the original thing, that is what we will get. So we will have del dot del psi, that is del 2 psi, and minus 1 over C square del 2A. This should be del psi by del T. So therefore, we will get del dot A plus del psi, and this is going to be del psi by del T2. So because this is supposed to be 0, 0, 0, this is anyway 0. So this means we will get 1 over C square del 2 psi by del 2. So this is the condition that, so this would be essentially fixing our Yes, so this restricts xi from being quite arbitrary. This will have a definite value of xi, which is essentially going to be again in the form of a wave itself, and therefore we will have a better form. Okay, so this is all about the vector and this is all about the gauge conditions. So in the next lecture, I will discuss about the solutions of phi and A, at least for the electrostatic case, and then we will move to the energy and various other parameters for these electromagnetic waves. Thanks for now. Stay safe.